Here we go. So we just finished doing this, the old doubly linked list. We can look at it horizontally. We could look at it, vertically, different ways to look at it. But we're used to this nice linear picture, and all of a sudden when we had all these other things going on, different ways to this arrow. And again, this arrow is holds the address. And I didn't used to emphasize it. I've gotten better. And this is simply the address. The address is stored in that location. Okay. So we went along. You did a program. Most of you did a really, really good job on it. And none of the code was really tough if you did well in that group the week before. And if you have pictures to understand what's going on. Right? So we went one direction. Now we're going two direction and so forth, doubly linked list, and it's all good. The programs, you had your menu up here in this upper left-hand corner of the screen, and it just kept scrolling and scrolling. Some of the good ones, they had a menu item over here, moved out in the middle. A lot of you had some, not some, a lot. Some of you had colors going on in here. Some of you used the clear screens. Some of you tabbed, some of you just use line spacing, but I'd like to see more and more of that pizzazz. Like if you were going to sell this, and there were times when we would be in a regular classroom and I'd tell everybody, pull your opening screen up and let it sit there. And then I'd give everybody three pieces of paper. They could go around and look for and vote for which one was the most user friendly within the class. And then I would give extra points out based on that. But yeah, get it out of this upper left hand corner. I don't want it up there. I want to be able to read it, not look up in the corner and give it some pizzazz. I like pizzazz. Okay, so what we're going to do today is take this doubly linked list, and it's funny because now we're going back to the Gaddis book. We're jumping out to chapter 21, and I explained to you that I think the way it's being taught is sequential. We learned about list, we did stacks and queues, now doubly linked list. And I disagree with the way the book is laid out. So I teach it my way, but I hope it's sequential in your mind. And we're now going to take this bad boy and we're going to build something called a binary tree. And instead of this being straight horizontal or straight vertical, depending on what you like in your mind. We're now going to take this and we're going to build something that's going to help us do searching. We're going to take this idea where I have a node, two pointers, and a value or values, and set it up in a way similar to this doubly linked list, but when it comes to searching, it's going to be a whole lot nicer. Well, searching, let's talk about what searching we've done. We've had arrays. We started at the beginning and went all the way to the end. A nice sequential search. We had an array where the values were sorted, right? Inside of here, they were sorted. And then instead of sequential, which stank because the worst case scenario is it was the last item in the list or not in the list at all. We had binary search. And to do that, we went to the middle one and played a little bit of a game of higher or lower. Was it higher or was it lower? But we had to sort before we could search. So up here was just a search, now you're getting into your big O notation. Here is a sort and a search, which you would think would take longer, except according to Big O, this search should be, if there's 16 items, I play higher or lower, I should find it in how many guesses?
Three.
Three or four, right? It's 2 to the X power. 16 is 2 to the fourth power. So if I cut it in half and cut it in half, it might be 3 or 4. But all of a sudden, my big O notation isn't the whole thing. It's going to be this log base 2 or 2 to the kind of idea where the searching is much faster, but we also had the sort going along with it. So, what are we going to talk about today? Well, a way to make searching a little bit faster. And now, when we get ready to store the values as we read them in, we're going to store them not in an array, but in a binary tree. Binary tree. Why is it called a binary tree? Well, it looks like this. And if I turn this upside down, here's a tree with all the flower or leaves going up. Down here's the roots in the ground. So when we're working with this thing called a binary tree, we're going to start at the root. The root is going to hold the address of the first node. Okay. So what is a binary tree? It's a nonlinear. Yeah, this isn't linear like before. I'm not moving left and right. I'm breaking off, going different directions. And we're going to see this the rest of the course. Some concepts that you thought were easy, like searching and sorting, and you could do them the best possible way. We're now going to open our eyes and see a lot of different options. So it's a linked structure, which each node can point to two nodes. Here's a node, it can point to two nodes. It can point to two nodes. You notice this node down here doesn't point to two nodes, points to two nulls. So we're going to have a structure similar to what we had for a doubly linked list, but we're treating it a little bit differently. Every node, except the root, has what's called a predecessor. But as you can see, we're going to have a little trouble trying to, we can get down, we can go down, but we're going to have trouble going backwards. We're going to see how that works. That gets pretty darn clever in a little bit. All right. So what's going on here? Makes searching larger sets of data a whole lot quicker. You like it? Not yet, because we don't know a whole lot about it. All right. First thing, let's figure out how we build one of these binary search trees. And again, this is going to make searching a lot easier. But the way we build it is going to be key. Now, we're building it one way today. In the future, you're going to see other ways to build it that make you go, hmm. All right. BST, a binary search tree. Binary 0 or 1, left or right. First letter, M, going to be at the top. M. If I wanted to make it look like a node, I could and have all kinds of arrows. But as we get better at this, you're going to be drawing it a little quicker. Now, the next letter is F. Where do I want to put the F? Well, remember the idea behind all this is searching. So I'm going to come up with a pattern where I know how to search based on how I built the tree. So here's M. I'm going to make F go to the left. Why to the left? Because it's smaller. Wow, that's really sloppy. R. R is going to go to the right of M. P. Well, that's greater than M. That's also less than R. So P is now on this third level. I have a B. It's to the left of M. It's to the left of F. And now I can put it in. How would I know I could store it there? Because F's, whatever we're gonna call this pointer, was originally pointing to what?
To null.
Yeah, it's gonna be pointing to null until I put something in. So now I'm gonna put B in. And yeah, this would point to null, and this would point to null. And basically, this goes back to the same idea as before. When I create it, I'm going to have null and null. I still have an S. I'm going to put S over here. So this is pointing to S. This is pointing to null. Oh, this would point to null. Null, null, null. Okay. So if I look at this binary search tree and I'd say, is there a C? You'd go, well, that's less than F or M. That's less than F. That's greater than B. Nope, there's no C. Much quicker than some of the other ways that we've been doing searching. Cool. How many values did I have to check? One, two, three. I only had to check 3 times. So let's see if I did a little work over here and I'd say, all right, and I'd say, okay, so for this first level, I believe I can store one value. If I look at 2 levels, I can store 3 values. 3 levels, how many values can I store?
4.
Total? For level 2, we went 1, 2, 3. So for level 3, 1,
6, 7,
It'd be 7.
7.
yeah, it would be 7. Okay, pre-calc. Sequences and series. I'm looking over here. If I had another level, how many could I store?
$15.
Yeah, 15. So within 4 looks, I could have 15 numbers stored. 1 looks. How many numbers can I have stored? My math experts.
31.
31. I said N. You took
Oh,
5.
sorry.
Yeah, it's okay. Absolutely okay. If it was 5, it would be 31. Yes, you got it.
It would be n minus 1 minus n minus 2 plus n minus 1. All
Minus
right.
1.
It would be n equals n sub 1, which would be the 15 in this case,
And sub
assuming we're
1.
using this chart, and then n sub 2, so 15 minus 7 would give you 8, and then you would add that to the 15 to get 23 for the next one, right?
Except the next one, 5 should be 31. Close. Close. I'm totally with what you were thinking.
I missed the multiplying by 2.
Mhm. It's in there somewhere. Two to the first power is 2 minus 1 is 1. 2 to the second power is 4 minus 1 is 3. 2 to the third power minus 1 is 7. yada, yada, yada. Bang. So if I said 10, if I had 10 rows, how many values could I store? What's 2 to the 10th power? Bam. It's a kilo.
1023.
Yeah. Yep. 1024 minus. So within 10 rows, I could store over 1,000 values. All right. So we have this new data type. This is a new data type. And whenever we come up with a new data type, like a stack, like a queue, like a doubly linked list, what do we need to do? Well, we need to come up with functions. But before we use any of these functions, is empty. Ah, how would I know if it's empty?
If the root points to null.
If the root is false, if it points to null, sure. Okay. How do I insert? Well, we're going to talk about that in a minute. We're going to, once we start, we move left or right down the tree until we find a null. How do we delete? Oh boy. Yeah, that's the crazy one. How do we do traversal? How do we display the list? Is there more than one way to display the list? But before we do any of that, I want you to build this tree to make sure we are all on the same page. I'm going to pause the recording so remind me to restart it. If I start to build this tree, there's a 5. Next up is 8. So I'm going to go over here with 8. 3 is less than. I'm going to go over here with 3. 12 is greater than 5, greater than 8. So 12 is going out here. 9, greater than 5, greater than 8, greater than 12. Less than 12. 4, dun, dun. And 6. Well, that ended up not too bad. It's kind of balanced. Down the road, we're going to talk about balancing a tree, where like it's sort of, I mean, you could see if I did 1, 2, 3, 4, 5 as my values, I'd have 1, then go to the right for 2, then go to the right for 3, then go to the right for 4, and so on, and it would get pretty messy. But that's not a bad looking tree. Root points to 5. You go from there. Okay. Well, I'm going to jump down and take a look at this traverse. And I'm going to talk about traversing the tree because we've already done traversals. We've already done traversals. And as soon as I write pre-order, in order, and post order, you're going, yep, I kind of remember those. And I don't. So I need to go. I'm going to go back to, yeah, let's do 4 plus 6. And that was this guy. 4 plus 6. And my pre-order was, the operation was first, plus 4 and 6. My in order was 4 plus 6. That was the original. And again, I see my 4 and 6 aren't moving, but the plus sign moved. Okay, that's right. I'm rebuilding this. And now I can go back to this being node left, right. Node left, right. Left, node right. Left, right, node. And I have that terminology. So if I want to now go back and traverse this list, I'm going to start with pre-order. Do you remember? Going to pause the record. Let's see if we got the first one. Node is 5. Boom. So I come to this location and it says node. So I'm doing 5. Then it says go to the left. Now I'm at this node, so I say 3. I go to the left, I hit a null, so now I go back, and I already did the node. The left was null, excuse me, and now the right is 4. This is a node, but there's no left, there's no right, so I go back. I already did the 3, so I go back. I now hit the 5. Now I'm coming down to its right because I did node, took care of the left, took care of the right. I hit a node, which is 8. I go to its left, which is a node. I hit a 6. I go to its left, which is null. Go to the left, right, it's null. So now I took care of the node 8. I took care of 8's left. Now I come down 8's right. I hit a node, which is 12. I go to its left, which is a node, which is 9. It has no left, it has no right. So I go back up to 12. I already did the node, I already did its left, and I check and there's no right. So 5, 3, 4, 8, 6, 12, 9. Does anybody have the answer for the in order?
Would it be 4, 3, 5, 6, 8, 9, 12?
At your list of numbers. Just take a quick peek at them. What do you notice about all your numbers but one? You started out 4, 3, and then you have 5, 6, 8, 9, 12. It's almost what? It's almost in order, right? Well, they should be in order. So let's see where we got. In order is left. So I go to the left of here. Left. I go to the left and there's nothing. Now I go back to the node, which is 3, and I go to its right. There is no left. I go back to the node, which is 4, go to its right. There is no. So I go back up here. I took care of left node right. This was 5's left. So I go back and this now becomes a 5. Then I go to the right. Now that I'm here, I go left, 6. Go back up node, 8. Right. I go to its left, which is 9. Go back up to its node. Check its right, and I'm done. Real close, Jack. That was a really good first try.
So on what the reason it's like actually in order is because when you go to the 3 node, when you go to its left, it's null. It's so we just don't even bother. Then we go back to the node that is 3.
Yep. And since it exists, we hit it. Then we go down its right, and we was so if there was 3.5, I would be at this node and I would go left before I display the node.
Got it. Thank you.
Sure. Post. Post. I say post. You say balloon. No, don't do that. That was
Is
a
that 4, 3, 6, 9, 12, 8, 5?
4, 3, 6, 9, 12, 8, 5. First thing I'm going to do is count 1, 2, 3, 4, 5, 6, 7. There's 7 of them. Let's see. I want to do the left, then the right, then the node. There's no left. There's the right, and then the node. I did the left. So now I'm going to do the. So if I did the left and now I'm doing the right, 5 is going to have to be my last number because it's going to come all the way back up to that node last. So 4, 3, I go to the right, I get to here, I go to the left, which is 6. I go over to the right. But now that I'm here, I go to the left, which is 9. There is no right, but the node is 12. Then I work my way back. The node is 8 and the node is 5. Perfect. Good.
So something like posted would be really good if you want to search down like a really long tree and get to things at the end first, right?
Yes. We also have other things going on. Remember what post that worked for popping and pushing but yeah. Now, what if I said, how would you write code to traverse this? How am I going, for example, 3, I can get to there. The 4, how in the heck am I going to get back to 5? I probably never could have come up with it. We're going to see it in a minute. But to start thinking about how could I traverse this is in order the most common traversal. Are there other uses for pre and post that we just don't know about yet? But we do know we may want to print this list out. And eventually, we're going to do something that's really cool. How would I? Now, this is a binary search tree. It's great for searching. Find 7. Nope. Your eyes are moving right through there pretty quick. Find 14. Bigger, bigger, bigger. Nope. Ha! Bigger. Who's bigger? Mrs. Bigger or Mrs. Bigger's baby? Mrs. Bigger's baby because it's a little bigger. It's a little bigger. Andrea, it's a little bigger. Get it? Yeah, okay. All right, I'll stop on that. Now I got a womp, 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 womp coming out of there.
Yeah, I thought that was hilarious.
Okay. All right. Oh boy. So we start thinking of the functions. For us to sit and say, let's write them as groups, it would take a long, long time. But since we're here, we might as well do a little thinking on it and see what we can come up with. And then we're going to look at the actual code in the book. And then it's one of those, yes, I own binary search tree and it can search and do wonderful things for me. Like add something, delete something, traverse the list, and so forth. I'm going to actually make this 15 because as I looked at my list, it was kind of dumb. 15 must have been the first number put in, and then either 18 or 17 or 7, and left and right, and then the 3. And if I just, I got all my nulls in here, and it's all good. So I want to delete a child, and I'm at 15, and I say, wait a minute, the number I want to delete is 7. The number I want to delete is 7. So I'm going to make notes in here to self. I want to delete 7. Okay. 7's unique because it only has one child. I'm going to do something like, this is just me thinking out loud. I'm going to have a temp pointer that is currently pointing to 15. I don't know if there was stuff before it or down there. I just know right now it's pointing at 15 and I'm looking for 7. So talk to me. What do we got here? And we're going to call these left and right, which are kind of obvious names. Instead of prev and next, it's going to be left and right. So the question that's going to be asked, if this is just one, part of it, if temp pointers we're going to trigger it, but if temp pointers left value equals that num, we're going to pretend it does. We're going to delete 7, so 7 is num. And I'm pointing right here. I'm like, yippee-ki-yay. Boom. Now, in order to be one child, we would need like the left or the right. We'd need one of those to be, oh man, we would have to think of situations like, what if 3 is the only child? What if the number 8 on the other side was the only child? How do I do each one of these things? And it's going to become a mess. But let's just say this became true. 10 pointers left's value equal to num. And we'd almost need like, and temp pointers left's right equals null. That would be this guy. Temp pointers left's right would equal null. Then I'd like to just. So yeah, I'm just making notes. So this would also be like, and temp pointers left right equals 0. So again, I'm just using a picture and I'm starting to draw out some code that might work. This is this one situation where I want to delete 7 and I have something to its left. And this left could be a lot of stuff. It could be a big subtree, right? If we have a whole tree, that would be a subtree going on down. What would my next line of code be?
Would you make heads left equal to heads
Don't
left?
worry about, hang on. Let's not worry about that being head. We're worrying about sitting here at temp pointer right now. And what I need to do is have this guy point somewhere.
So temp pointers left then would equal temp pointers left left?
Temp pointers left. That's this guy. That's this address. Temp pointers left would now get temp pointers left, which is that address. So this guy would now point there. And again, we could have something saved so that we can delete the node from memory if we want. Quite a few of you did that in the last program, which is a good job, freeing up the memory. But I just wanted to look at a situation like that. Again, this is one child. Remember, we could delete this head. We could be deleting one child where it has one child to the left, one child to the right. We could be deleting something that has 2 children. What if I said, now delete 7? How's this guy going to work? But we're just taking this giant program and breaking it down into different situations. I need to understand the situation and then I can write the code. This part's the easy part. Drawing the picture and figuring out what you want to do is the bizarre part. Okay, so now I'm sitting with temp pointer is pointing to this node. Don't know where it came from. Came from somewhere, but it's sitting there. And I just found out that 7 is what I want to delete. and the left does not equal to null and the right does not equal null. I'm looking at temp pointers left value and I'm going, woohoo. And like in the previous case, its right was null. So I went from there. We talked about what if its left was null? You know, that would be very similar to what we just did. But what if both of them have values? Which one should be up here? The 3 or the 8?
The 8, right?
The 8's a good guess. Why?
Because it's the larger value.
Yes, because it's larger. If I put the 3 here, it wouldn't make sense because as we've been building these, we had the larger value on top. The larger value, the larger value. Well, not always. Not always. But the 8 is what we want to move up there. So if I was to start drawing lines, what would end up happening is tell me what I want, what I really want. I want 15 here, and I now want to go down to 8. And that 8 would go down to 3 and everything that has it. But what would be here? What would be there?
7.
Well, 7's what we're deleting. So we're looking to delete 7.
So we're back to null again, then being attached to 8.
Okay. What if there's values here? What if I had 7.5? Where would that go?
So then it has to do, you have to like obey the structure. So it would be whatever number is like greater than the other number stored on its left or right.
So what's going to happen is this. And, you know, we should probably have had a node down here. This guy is now going to point here. This guy all the way down to the left, as far down as I can possibly go. You know, there might be more nodes, and until I hit that last null, we'll then go and point to here. Seven's going to go, 8's going to attach there, and then we need to search down here till I hit a null to attach that side. Again, here it's just one case because it hit null, but what if there was something else here, like 7.5? Okay. I have 2 lines here. And I have to be careful. I don't want to lose this guy. So I think I'm gonna, I need a pointer to here. So what's gonna happen?
Would you make, in this instance, temp pointers left, right, left be equal to temp pointers left, left?
I'm gonna write it down and then look at it. Temp pointers
Left,
left,
right,
right,
left
left,
equals temp pointer left, left.
temp pointers left, right, left equal temp pointers left, left. Yep. Now that's going to be this one case because I found the null. But I would need a way to get down to the null as far left as I can before I attach it. So my second line would then be what? Anybody else?
So it wouldn't matter what other values extended from the 8, you would always connect the 3 at the bottom.
Yes. So if there was 7.5 and then 7.4 and
And
then
then
null,
2.
that's where it would get connected.
What if it was 2?
2 would be over here to the left of 3.
Then it wouldn't. Okay.
Yeah. Last part here's temp pointers. This guy, this address.
What
Anybody?
about making a doubly linked binary tree?
Oh, go away.
What? That seems like a more efficient way to do it. I mean, you're not limited to just 2 pointers.
Oh, no, you're not. And eventually we're going to see nodes that could have 3 pointers, 4
Yeah.
pointers. And the 4 pointers, we could store 3 values in here because we want to go in between them and 4 point. We're going to get to all of that. But I've never heard of a doubly linked binary search tree.
If I do that for the project this week, are you going to get mad at me?
I never get mad at you. I might say you're a little muy loco in la cabeza, but
Well, that's fair.
aren't we all, right? Finish this for me.
Do you want me to go again?
Yeah.
Temp pointer left equals temp pointer left right.
That's correct. Participation in sport goes much faster when you're participating. Wouldn't you agree? All right. So yeah, you got, man, all of a sudden the eyes open up. We got this binary search tree. We have a lot of code to write unless it's written for us. And you on D2L will see you are now the fine owners of int binary tree. You'll be the fine owner of it once I figure out how to make it work for sure. Yeah, I understand that as well. Here's our struct. Here's our struct. Makes sense. Left and right instead of prev and next. Tree, we have root. We called it root. We called it head and something else. We had a bunch of different things going on. Our functions, right? Our specification file, we're going to lay out our function insert. Oh, an address and an address. Destroy. That's something with a value. Delete node. Have an integer and I have an address. Make deletion. Oh, look at these 3. Display in order, pre-order, and post-order. That looks kind of interesting. Okay. What do I have? A constructor, boom. A destructor, boom. I have, timeout, Bubbaloo. I have privates up here. All of these functions are private. Down here, I have public ones that kind of have the same name. There's insert, there's search, and there is remove. So what's going to happen is these guys are going to get called in your demo program. And then you're going to see what happens within these and how it's related to these. I'm so excited. I can't wait. Couple of more public functions. Display in order, pre-order, and yeah, yeah. Display in order, display in, okay. I gave you the hint. Right there it is. I have a function, and inside of the function, what's it calling? 6-letter word, starts with I.
Itself.
Itself, right? And when I have a function calling itself, we have recursion going on. What's going on? What's going on? Insert. All right, just breaking down, looking at a couple of blocks of code. I create a node and I take that root. This is the first part. This is where the root is. What's being passed here? The address. What's being passed here? The new node that was created. So I want to insert, I'm going to bring in a value. I'm going to store it in a node. I'm going to call this other function insert. I'm going to send in the address of where I'm currently at as I move through. That's going to be like temp pointer kind of deal. An address, and this holds that current address of new node. So I have this public insert node that's going to call this private insert. Ooh. The private insert. This is where I'm currently at, the root. This is the new node. What's going to happen is this is going to keep changing until I find a place to insert new node. I'm going to keep calling this insert. If node equals pointer, ba-boom, I get to put it in there. If it doesn't, I'm going to, if it's less than, move down to the left address. If it's greater than, move down the right side. Oh, isn't that clever little code? I don't think I could have ever come up with it without hours of work. But if it does equal that null or zero or cap null, yeah, I come in to insert it. I'm going to go until I find a null pointer. And then the current node pointer is going to get the value of new node. Right? That's going to be from up there. That's pretty darn clever. Program 21.1. This is great. You could go and fill it with insert node 5, 8, 3, 12, and 9, but it doesn't do you much because that's all we got. We don't have a way to print it out yet. We actually are going to have 3 ways to print it out. What are the 3 ways? Well, let's see. We just talked about in order, pre-order, and post-order. And let's see what's going on here. So this guy is in order. And in order was left, node, right. Check this out, how it winds itself down that left path until it can't go anymore. And then it does the value, but it's going to rewind itself out through the lefts, printing out. No, oh, man. This is going to give us an in-order display. Tell me which 2 lines I would switch for a post-order display. And again, each time we're displaying what's at the node, the left and right are just telling me to keep moving.
Would you just switch the arguments for the recursion?
Now, which 2 lines would I switch?
158 and 160.
That would give me right node left. I don't want right node left. For pre-order, I'm going to do the node, which is what I want to display, then the left, and then the right. So these are really stinking clever, how they traverse down through there using recursion. Yeah, and then out here's post order. Post order, the node is going to come last. Left, right node. So program 21.2 does the inserts, and then it's going to display the traversals. So in our program, but we had some numbers that looked like this: 5, 3, 8, 4, 6, 12, and 9. And if we ran 21.2, we might have to change. What is this? Oh, look at that. 5, 8, 3, 12, 9. I actually have 4 and 6 in the list because I wanted a little bit more. So if you loaded up 21-2, you added 2 more lines, insert node 4, insert node 6. Do you get what we had with pre-order, in order, and post order? Again, I was 2 lines short. I added an extra 4 and a 6. So I used recursion to insert. I used recursion to traverse. Now that I've seen those, they are clever little buggers. The big one coming up next is delete. And we know there's going to be so many situations. What if it's the root? What if it has 1 child? What if it has 2 children? What if it has no children? That should be easy. We just make a point to null. Logan, did these numbers work? You can just nod. Okay, looks like you had it done. That's why I asked.
Quick question.
Yep.
When you're doing like a deletion, does
Mhm.
that mean you always have to kind of have like 3 cases to check? Does it have children? Does it have 1 child? Does it have no children?
Yes, and I'm thinking also, what if it's the head?
Oh, right.
And then what if I said delete 6? Or excuse me, delete 10. Does it always mean we keep moving left and right to null? Or, so make sure you're thinking through all the situations. Are these the right answers for pre, in, and post?
Yes.
Good, good. All right. Do. So the last thing to look at, yeah. And if you didn't like, when we were talking about it in class, and you notice how they do value left pointer, right pointer, we drew ours a little different. It's up to you, however you want. But you can start to see things like, if I'm going to knock something out. And again, the author's drawing pictures, not just me. And how we go here, and then that bounces back over there. We kind of talked about all those things. And we see deletion. Yeah, if it equals null, then yeah, that's good. And we got going down the right. We got reattaching the children, on and on and on. If it has 2 children, we got a whole lot of shaking going on. Why there's such a glare there? That's better if I do that. Reattach the left subtree. Reattach the right subtree. Well, that documentation is kind of nice. We did something similar to this. What we did in that situation was right, but the way this code was written, it went a little more in slickness. But the good news is you now own binary int tree. Oh, where is it? Where is it? Right here. You own int binary tree, the spec file, and you own the implementation file. Okay. Your next program is available now. It deals with binary trees. On Wednesday, we're going to do a little more work with binary trees. It's kind of cool. But as we go, we're going to see different manipulations of the nodes, what we can put in there more than just 1 value and 2 pointers. Andrea would like to put 1 value with 4 pointers. We're going to see where we'll put multiple values with multiple pointers coming up down the road. No need to play with this today. That was a lot to wrap your head around. Are there any questions? And if not, we're going to put a wrap on that for today. Make sure you read the program and let me know if you have any questions on Wednesday about it. And we will go from there. 15 classes down and 13 to go. All righty. Yeah, Jack. Okay. Have a good day. I'll see you on a Wednesday.
But I had a quick question I didn't get to ask because
Yeah, Jay.
so when you did the level part with the storing, you said it was I didn't when you said so it was 2n minus 1. But how is it minus 1 when it's
So what is 2 to the third power? So
2 to the
2 to the third power is 8 minus 1 gets me to 7.
mm-hmm.
2 to the fourth power is 16 minus 1 gets me to 15.
Okay. But like where's the like in like level 2, where's 0.3 in the picture? Or like
1, 2, 3. It's the total number of values we can store.
oh
So in the first level, we can store 1. In 2 levels, we can store a total of 3 values.
oh okay.
In 3 levels, 1, 2, 3, 4, 5, 6, 7, we could have scored 7 values.
Okay.
I had 10 levels, I could have stored 1,023 values, which mean if I was searching through here, I'd get there pretty quick to find out if it's there or not.
Yeah. Okay. Okay, I get it now. Okay.
Cool. Okay,
Thank you.
you bet. Yes, sir, Mr. Jack.
You're still recording, just so you know.